section, I'd like to talk about equilibrium expressions that involve pressures. So, we've seen so far that equilibrium expressions include concentrations of reactants and products expressed in moles per liter, but the expressions can also involve partial pressures of gases if the reaction occurs in the gas phase. So, for example, in the ammonia synthesis equilibrium, I can write the equilibrium expression, as we've done in the past, the concentration of ammonia squared divided by the product of the concentration of N2 times the concentration of H2 to the third power. K sub C is used to indicate a K expression expressed in terms of molar concentrations. If you see just K equals, that implies K sub C. So sometimes the C is there and sometimes it's not. But if the C is there, it definitely means in terms of concentrations. But if I measure the relative amounts of reactants and products in terms not of the molar concentrations, but of the partial pressures in atmospheres, I can write the Kp expression. Kp equals the partial pressure of ammonia squared divided by the product of the partial pressure of nitrogen and the partial pressure of hydrogen cubed. So the question is, how are K, or Kc, and Kp related to one another quantitatively? Well, assuming ideal behavior, which is not a good assumption, but we're going to make it anyway, we know that the concentration of component A is equal to the moles of A divided by the volume. Well, rearranging the ideal gas law, that simply gives us the partial pressure of A divided by RT. So, let's do the derivation in which we calculate Kp as a function of Kc. Let's begin with a generic equation. A moles of A in the gas phase in equilibrium with B moles of B in the gas phase. I can write my Kc expression as the concentration of B to the B power divided by the concentration of A to the A power. I will substitute in place of concentration partial pressure over RT. So this gives partial pressure of B over RT to the B power divided by the partial pressure of A over RT to the A power. Okay? I'll factor out the RT terms, and I get the partial pressure of B to the B power over the partial pressure of A to the A power times 1 over RT to the B divided by 1 over RT to the A. Well, we can see that partial pressure of B to the B power divided by partial pressure of A to the A power is simply Kp. So Kc equals Kp times 1 over RT to the B minus A power. I don't like that 1 over RT, so I will flip it and reverse the order of the exponents. This gives me Kc equals Kp times RT to the A minus B. That's Kc as a function of Kp. Let's now get Kp as a function of Kc. Kp equals Kc times 1 over RT to the A minus B, which is equal to Kc times RT to the B minus A. Okay? Now, that's B minus A. B minus A is the coefficient of the product minus B sub A, B minus A is the coefficient of the gaseous product minus the coefficient of the gaseous reactant. So I can summarize this as Kp equals Kc times RT to the delta N. There is my equation, for which delta N equals moles of gas product minus moles of gas reactant. Or more specifically, the sum of the coefficients of all of the gaseous products minus the sum of the coefficients of all the gaseous reactants. Okay. Before we do a problem with that, let's ask the question, if we manipulate an equation using the Kp expression, can we calculate new Kp values as we did before with Kc? Well, the answer clearly is yes. Okay? So for the synthesis of 2 moles of hydrogen bromide from its elements, we're given a value of Kp at a certain temperature. What is the value of Kp at the same temperature for the following reaction, which is the decomposition of 1 mole of HBr into its elements? Well, we can see that we did 2 things. First of all, we reversed the equation. So that means we invert or take the reciprocal of K. And we also multiplied the the equation by 1/2. So that means we take k to the 1/2 power. So k sub p prime is going to be 1 over the square root of the given k sub p, which is 1 over the square root of 3.5 times 10 to the 4th, which is equal to 5.3 times 10 to the negative 3rd, which would be kp prime for the manipulated equation. From the previous video, you may recall we calculated a value of K or Kc for the synthesis of 2 moles of dinitrogen monoxide from its elements. We got a value of Kc equals 4.08 times 10 to the 8th. So let's calculate the value of Kp for this reaction. Kp equals Kc times RT to the delta N. Delta N in this case is equal to the sum of the coefficients of gaseous products minus the sum of the coefficients of gaseous reactants, or -1. So to plug in, 4.08 times 10 to the 8th times R, the gas constant, 0.08206, times the temperature, 425 Kelvin. Sorry. Raised to the power of delta N, which is -1, which gives me a value of Kp equals 1.17 times 10 to the 7th. And this is the value of Kp you would use if you were doing equilibrium calculations using partial pressures rather than molar concentrations. In this section, let's talk about heterogeneous equilibria. Heterogeneous obviously means different phases. These equilibria are reactions that are involving more than one phase, and usually it's gases and solids. So here's an example. If I have solid calcium carbonate, which is limestone, in a sealed container, in a vacuum, it will undergo decomposition to form solid calcium oxide and carbon dioxide gas, and this is an equilibrium process. If I write out my equilibrium expression for it, let's call this K prime, will be the concentration of calcium oxide times the concentration of carbon dioxide divided by the concentration of calcium carbonate. Okay? Well, I understand the concentration of carbon dioxide, but what does it mean to talk about the concentration of the solids, calcium oxide and calcium carbonate? I guess you could calculate a concentration in moles per liter of solid using densities and molar masses, but those concentrations don't change. So let's replace the concentrations of the solids with just some generic constants. Let's call this C1, and let's call this C2, sorry. Okay, well, I can simply rearrange by collecting all of the constants, and I get K prime times C2 over C1 is equal to the concentration of carbon dioxide, which is really the only concentration that can change. So that's going to be our actual equilibrium expression. Okay, so take-home lesson is as follows. You should leave out pure solids and pure liquids from the equilibrium expression because their concentrations are constant and hence are lumped into the equilibrium constant K. When you're writing equilibrium expressions, only include those species whose concentrations in moles per liter or partial pressures in atmospheres do not change. And generally that's going to involve gases and aqueous solutes. So in this reaction, iron is reacting with water vapor to form magnetite, Fe3O4 plus hydrogen gas. At a given temperature, it is observed when the equilibrium partial pressure of water vapor is 15.0 torr, the total pressure is 36.3 torr. Calculate the value of K sub P for this reaction at 1200 K. So let's first begin by writing out the Kp expression. Kp is equal to, leaving out the solids, this is simply equal to the partial pressure of hydrogen gas to the 4th power divided by the partial pressure of water vapor to the 4th power. And if you want to simplify your lives, you could combine that and say pH2 over pH2O to the 4th power. Okay? Now, we are given the partial pressure of water vapor, and we're given the total pressure. How do we calculate the partial pressure of hydrogen? Well, we're going to be using Dalton's law of partial pressures, of course. pH2 equals P total minus pH2O equals 36.3 torr minus 15.0 torr, or 21.3 torr. So now I can simply plug into my Kp expression. Kp is the partial pressure of hydrogen divided by the partial pressure of water vapor raised to the fourth power, or 4.07, is my value of Kp for this reaction. Okay, that's it for Kp and heterogeneous equilibrium problems. In the next video, we will talk about more detailed equilibrium calculations. See you then.